There was yet another series of articles in the mainstream press last week that the Mediterranean diet is the best thing ever, but there are rumors on the internet that perhaps olive oil causes weight gain. This is compounded by the fact that the Greek philosopher Plato said that olive oil is a very great evil to man's inward parts, and for this reason physicians always forbid their patients the use of olive oil in their food. Strange thing to say for a miracle fat. And it doesn't take long in the medical literature to see that the highest rates of obesity in Europe are in Greece, Spain, and southern Italy, which is weird because isn't that where they grow olives? And sure enough, if you dig in, you'll see that the obesity really is in southern Italy. You can see the dark areas there. That's where all the way back in the time period from 1998 to 2002, 33 to 39% of the women were obese. And you think that seems very high. What were the levels in the US back then? And it's only 20%. So rural southern Italy already had a larger obesity problem than the US all the way back in the year 2000. Further perusing the medical literature will prove to you that indeed they consume more olive oil in southern Italy than they do in the north where they eat butter. In this European study into body mass index and waist to hip ratio, the authors concluded that overweight is a genuine problem in Greece and perhaps other Mediterranean countries, which is interesting in and of itself. And they say that adherence to a Mediterranean diet, and that means olive oil, is essentially unrelated to BMI, which means it's related, right? And also you seem a little defensive. They go on to say, though, the problem isn't the olive oil, it's the fact that the people in the Mediterranean are lazy and they're gluttons, which is a funny thing to say because why aren't the ones who eat butter lazy gluttons? So then in 1998, someone decided to test this in the lab. You know, before you launch a drug, you do a preclinical trial. In this case, it was more of a post-clinical trial because they'd already been recommending the olive oil for 40 years or so. What they found was that the mice on the olive oil diet actually consumed less calories and became fat. More concerningly, their blood glucose and insulin levels were significantly higher than the mice on the high carbohydrate diet. This suggests that something about the olive oil gave these mice insulin resistance. As a further test, one group of mice was fed something called high triolein. That's an oil that is almost purely oleic acid, which is the monounsaturated fat, which is prominent in olive oil. But olive oil, of course, has some saturated fat and some polyunsaturated fat, and also a lot of things like polyphenols, which have interesting effects. So by feeding the mice an oil that's pure oleic acid, you can get rid of a lot of those other variables. And what happened is the mice who got pure oleic acid were even more insulin resistant, having even higher blood glucose and higher fasting insulin levels. Why does everyone like olive oil in the first place? If you give someone a breakfast containing monounsaturated fat, they'll burn considerably more fat after the meal and less carbohydrates. And that sounds pretty good, you know, burn more fat. And you can see that on the chart here is respiratory quotient. A lower respiratory quotient means you're burning more fat. So you can see people who ate olive oil with their breakfast did really burn more fat. The problem with this is that obese people also have a lower respiratory quotient after they consume carbohydrates. Obese humans favor the burning of fat over carbohydrates, so we can say that the olive oil made the metabolism of the lean people more like the metabolism of fat people. When you consume olive oil, your intestines release something called OEA, which suppresses appetite by stimulating satiety. And that also sounds pretty good. But the problem is in the lab, if you give mice a diet high in fat for a week, they stop producing the OEA. They also stop producing it if you feed them too much sugar. So it's not clear if OEA is something that we can rely on. The other thing that olive oil has that might be beneficial is polyphenols. So in this study, they gave people high polyphenol extra virgin olive oil, and its consumption significantly reduced fasting plasma glucose, HbA1c, as well as BMI and body weight. Don't worry, it did not reduce BMI and body weight by any significant amount, a couple of pounds maybe. But the flip side of this is that the refined olive oil did not have any of these benefits. But what the study does tell us is if there are any benefits to olive oil, it's probably in the polyphenols and not in the oil itself. Anyway, back to the first dietary study in Europe where they called the people lazy gluttons. What they said is that when energy intake was not controlled for, what they mean is controlled for by their statistics. So in fact, people in the Mediterranean eating olive oil consumed more calories and became fat, which to me sounds like they're hyperphagic. Mammals who live outside of the tropics and some mammals who live in the tropics go through different parts of the year. You can see that grizzly bears in their active season from April through August have an active sort of a normal metabolism, but in the fall they become hyperphagic and on their way to insulin resistant. You can see the October bear there, chubby with a low body temperature. What month are you? I've always been in October. Anyway, what do the bears eat to get insulin resistance? Well, most years by mid-July they start eating pine nuts, which are full of PUFA, but also quite a bit of monounsaturated fat, plus fruit and ants. But in some years, there's not a good pine nut crop, and in those years, they eat significantly more ants along with their fruit, but also human garbage. See, bears are funny. And so you're wondering what ants are made of, and the answer is mostly mufa, with a fair amount of PUFA and not much saturated fat. That same study showed that the hyperphagic bears have upregulated lipogenic enzymes, and the word lipogenic means fat making. And you see those 4 enzymes, glucose 6-phosphate dehydrogenase is up by 1.7 times. That means 70% higher. Malic enzyme is 50% higher. Fatty acid synthase is almost 2.5 times as high. And ACC is more than 2.5 times as high in the bears earlier in the summer when they're in the active season. They also have significantly higher levels of these 3 enzymes, which are called desaturase enzymes, whose job is exactly what it sounds like. SCD1, the one that's 90% upregulated in the fall, adds a double bond to saturated fat, turning into monounsaturated fat. The other 2, D6D and D5D, are involved in adding more unsaturated bonds to polyunsaturated fat. Natambi found in the lab that mice who lacked the desaturase gene, SCD1, were incapable of becoming fat. They actually ate significantly more calories than normal mice and never become fat, no matter if the diet was low fat or high fat. Conversely, normal mice on a diet that's high in monounsaturated fat become obese. If you read that study, you'll see the high monounsaturated fat they used to make the mice obese was lard. And you've probably heard that lard is high in saturated fat, but that's actually just a nutritionist joke. Lard is actually high in monounsaturated fat. Those nutritionists are so funny. What Natambi also showed is that fructose and monounsaturated fat have a reinforcing fat on increasing liver fat accumulation and expression of the desaturase gene SCD1. He also showed that monounsaturated fat added to a culture of human liver cells increased the expression of an enzyme called SREBP1, which is the master regulator of lipogenesis in humans and other animals. So monounsaturated fat increases the expression of the lipogenic program. This creates a positive feedback loop because, of course, one of the lipogenic enzymes is SCD1, and the product of SCD1 is monounsaturated fat, or MUFA. So lipogenesis creates MUFA, which upregulates SREBP1C, which increases lipogenesis. To confirm these results, researchers tried the same experiment in worms called C. elegans. When the researchers removed the enzyme that allowed those worms to create monounsaturated fat, the worms could no longer store fat. But if they fed them oleic acid, the worms could store fat again. So they showed that monounsaturated fat is necessary for animals to store fat. More recently, researchers cultured human liver cells and fed them either monounsaturated fat or saturated fat, and showed that there's significantly more fat accumulation in human liver cells fed monounsaturated fat. If this is true, we should be able to show that animals in the lab fed monounsaturated fat have upregulated lipogenic enzymes. In this experiment, rats were fed diets with 40% of calories from fat as either olive oil, high in monounsaturated fat, sunflower oil, high in polyunsaturated fat, palm oil, which is a blend of saturated and monounsaturated fat, or beef tallow, which is mostly saturated fat. All the rats consumed the same amount of calories. The rats fed saturated fat gained the least amount of weight and had the least amount of liver fat accumulation, and the rats fed olive oil had the most liver fat accumulation. But the biggest finding of the experiment was the massive upregulation of enzymes involved in lipogenesis in the rats fed olive oil. The rats who consumed olive oil had a far higher expression of lipogenic enzymes than rats fed either polyunsaturated fat or saturated fat. An amazing thing about this experiment is the incredible similar expression pattern of lipogenic enzymes to the rats fed olive oil and the bears eating ants in the late summer to become hyperphagic. Perhaps the gluttons in the Mediterranean consuming olive oil are also hyperphagic. If you don't think rats are close enough to people, what about pigs? Pigs are about the same size as humans. They're also omnivores. What happens if we give pigs olive oil versus a saturated fat beef tallow? Not much, only 5% of the total diet. That's probably around 12% of calories. These oils were fed to 2 different breeds of hogs, a breed that's normally lean and a breed that is normally a fatty breed of hog. Regardless of the diet, the fat breed of hogs did indeed accumulate more fat, but in both breeds, the hogs given olive oil accumulated more fat than the hogs given beef tallow. But the amazing thing about this experiment was the explosive increase of lipogenic enzymes in the fat tissues of the fatty breed of hogs that were fed olive oil. Regardless of the breed, The hogs given olive oil had significantly higher expression of lipogenic enzymes than hogs fed the saturated beef tallow. How does this all work? We consume polyunsaturated fats as a fat called linoleic acid. That's it there at the top where it says soybean oil, LA. Linoleic acid is converted by the desaturase enzymes, which I mentioned is upregulated in the hyperphagic bears, D6D and D5D, and that converts the linoleic acid to arachidonic acid. Using mice in the lab, you can show that monounsaturated fat increases the expression of both D6D and D5D. You can see there again, triolein. That is pure oleic acid monounsaturated fat. How much did that take? About 7% of their diet. It doesn't take that much. So we can say that the expression of D6D and D5D are increased by olive oil. So if you consume monounsaturated fat and polyunsaturated fat, you will convert more polyunsaturated fat to arachidonic acid, AA. The study that I took this diagram from found that in obesity, individuals were almost 15 times more likely to have elevated D6D activity than lean individuals. Moving further down the chart, arachidonic acid gets converted to molecules called 5-heat, 9-heat, and 11-heat by an enzyme called cytochrome P450 1B1 or CYP1B1. The expression of that enzyme is controlled by a nuclear receptor called the aryl hydrocarbon receptor, as you can see here. So actual walking around obese humans were found to have 24 times as much 5-heat as lean humans. It seems that 5-heat might actually form a positive feedback loop with the aryl hydrocarbon receptor, activating the aryl hydrocarbon receptor so that it makes more CYP1B1, which then makes more 5-heat. Mice that don't have an aryl hydrocarbon receptor gene have significantly less 5-heat than mice who have one. If you've been reading the news, you may have heard that they burned a train of vinyl in Ohio. This quite likely released a cloud of dioxin. Dioxin is another environmental factor that activates the aryl hydrocarbon receptor, but I wouldn't worry about it unless you live in this red shaded area. Another interesting thing in this diagram is 15 heat, which the researchers found was 5-fold elevated in obese humans. 15 heat is interesting because it activates another nuclear receptor called PPAR gamma. PPAR gamma activates the lipogenic program by activating SREB-P. In the lab, we can show that a pharmaceutical activator of PPAR gamma, rosiglitazone, equivalent to 15 heat, causes weight gain in mice with less calories. Also insulin resistance. Rosiglitazone's a lovely drug, makes you gain weight until your heart explodes. We can show that this pathway is causal in obesity and not just associated with it, because if you break some links in this chain, for instance, the aryl hydrocarbon receptor, using a pharmaceutical, you can reverse obesity in mice. If we block the sequence of events higher up there at D5D using another pharmaceutical, mice will quickly lose weight while consuming the same number of calories. This study did a side-by-side comparison of D6D and D5D in mice consuming a high-fat diet composed of either mostly monounsaturated fat or mostly saturated fat. In this experiment for saturated fat, they use coconut oil and butter, so there's no jokes here. The saturated fat diet actually contains saturated fat, and the monounsaturated fat actually contains monounsaturated fat. What they found is that the mice on the monounsaturated fat diet actually consumed less food and had the highest metabolic rate, so they should have shredded abs, right? Well, not so much. Their body composition is actually a little fattier than mice on the high carbohydrate diet who consumed more calories and had a lower metabolic rate. But none of the mice in this experiment really got obese. The difference between the high carb fed mice and the butter fed mice is like the difference between the Japanese and the French in 1960. But the mice fed the monounsaturated fat again have elevated blood glucose. When they looked at the expression of D5D and D6D, sure enough, the mice on the high monounsaturated fat diets have significantly increased expression. And interestingly, the mice fed butter and coconut oil actually have significantly decreased levels of D5D and D6D. D6D activity is actually very relevant in humans. The EPIC study in Europe found that individuals with the highest D6D activity were 2.5 times as likely to develop diabetes over a 5-year period as those with the lowest D6D activity levels. The study also reported on the phospholipid composition of the mouse membranes. Researchers used something called the DNL index to know how much lipogenesis something is doing. DNL stands for de novo lipogenesis, and it's the ratio of 16O, which is palmitic acid, the 16 carbon saturated fat, to 18,2N6, which is linoleic acid. You can see that in the mice consuming the monounsaturated fat, the DNL index was 2.33, but in mice consuming saturated fat, the DNL index was only 1.96, indicating that the mice eating saturated fat were doing significantly less lipogenesis than the mice consuming the monounsaturated fat. This is relevant in humans because the DNL index predicts both BMI and waist circumference in women and men. Very simply, this is the process of de novo lipogenesis. The lipogenic enzyme fatty acid synthase, you can see it there, the FAS, takes acetyl-CoA and converts it into palmitic acid. Another elongase enzyme called ELOVL converts that to the 18-carbon stearic acid, and SCD1, the desaturase, desaturates that into 18,1-oleic acid, the monounsaturated fat. If lipogenic enzymes, including fatty acid synthase, are increased, you produce a lot of palmitic acid, and you can see that palmitic acid will be up in the phospholipid membranes. De novo lipogenesis also produces some myristic acid, a 14-carbon saturated fat. It doesn't produce a whole lot of it, but it's useful as a marker, which we will see in a minute. The researchers also found that the mice consuming monounsaturated fat have a very low level of EPA. In humans with diabetes, EPA is negatively associated with total mortality. So that means if you're in the lowest category of EPA levels, you're more than twice as likely to die. And the monounsaturated fat diet decreased the EPA levels of the mice. DGLA of the mice consuming monounsaturated fat is elevated. In humans, high DGLA is a significant predictor of insulin resistance in white people, black people, Hispanic people, and probably in Chinese people, although there were not enough Chinese people in this study for it to reach statistical significance. But does dietary oleic acid actually cause an increase in lipogenesis in actual humans? This is an excellent study. This study was done at a residential home for elderly persons where the diets of all of the participants were controlled. Since the cafeteria provided all the meals for the subjects of the experiment, this removes a ton of the variables that you often run up against when you try to do experiments on humans. This residential home normally used sunflower oil to prepare all of the meals for the residents, which is very high in the omega-6 linoleic acid. During the test, they swapped out that high linoleic oil for virgin olive oil, which is very high, of course, in oleic acid, monounsaturated fat, or MUFA. The results of the olive oil in the diabetic group were not that interesting, but in the healthy controls, the study reported phospholipid membrane composition, and you can see that there is a 50% increase in delta-6 delta activity. You can use these indexes to tell which enzymes are very active. In a reaction, you have a starting molecule A, which is converted to an ending molecule C by enzyme B. What happens is if the activity level of enzyme B is very high, then C goes up and A goes down. You can see in this diagram 18,3 omega-6 GLA, which rarely gets reported on, goes from 0.26 on the basal diet of sunflower oil to 0.37 on the olive oil diet, and GLA is the end product of delta-6 desaturase. The D6D index is an indirect measure of enzyme activity, but it did predict massively increased diabetes risk in the EPIC study. The participants in this experiment also had a significantly increased DNL index. So you see palmitic acid goes from 22.4 up to 24. These people were consuming olive oil, so it's not like they were eating a lot of palmitic acid. The palmitic acid must have come from de novo lipogenesis. So there's another excellent study done on the effects of membrane phospholipids if you feed patients canola oil. This experiment was done on young men in a metabolic ward. All meals were prepared in a metabolic kitchen. Canola oil is majority monounsaturated fat, but it also has a significant amount of PUFA, as much as 30%. The composition of canola oil is actually very similar to ant fat. Remember those hyperphagic bears? The participants in this study were fed a baseline diet that used mostly butter, but also some seed oils for 3 weeks. Then phospholipids were tested. Then for 8 weeks, they were fed a diet based on either canola oil or safflower oil. All of the diets had about 40% of their calories as fat. The plurality of the baseline diet was composed of saturated fats. In the canola oil diet, the majority of fat calories were from MUFA, and in the safflower oil, the majority of fat calories were from PUFA. Let's start with the safflower oil-based diet. In this experiment, you can't really go by the DNL index because the safflower oil diet is mostly linoleic acid, and that's part of the DNL index. However, since these diets are completely controlled, and we know that the diet that the patients are consuming has a massively decreased amount of palmitic acid in it, going from 17% of the fat in the baseline diet to only 8.5% of the fat in the test diet. If palmitic acid goes up, we know that that palmitic acid came from de novo lipogenesis. And as you can see, palmitic acid goes from 19.7 at baseline to 20.46 at week 3, and then all the way up to 22.66 in week 8. So the people on the safflower oil diet are definitely doing more de novo lipogenesis than when they were on the butter diet. Furthermore, as I said before, myristic acid, the 14-carbon saturated fat, is also produced in de novo lipogenesis. Now, there is some myristic acid in butter, but there's almost none in safflower oil. So in this test, myristic acid went from 5% of the baseline diet to 0.5% of the test diet, and yet the myristic acid in the membranes of the people goes up, and it goes up pretty significantly from 0.4 at the baseline all the way up to 0.65 in week 8. That is more than a 50% increase. The only place that myristic acid could have come from is from de novo lipogenesis due to the safflower oil-based diet versus a saturated fat diet. These researchers used isotope tracing to confirm that myristic acid and palmitic acid are indeed increased in humans who are doing more de novo lipogenesis. So with that in mind, let's look at the canola oil diet. If you really want to switch on de novo lipogenesis in someone, give them a diet where the base fat activates D6D and D5D, but that contains significant amount of polyunsaturated fat. That's what canola oil is in people, and that's what ants are in grizzly bears. The level of myristic acid in these young men in a metabolic ward explodes when you give them canola oil, nearly doubling over the 8 weeks of the experiment. Palmitic acid also increases massively, 20% over the course of the experiment, and palmitic acid was already at 20% to begin with. And of course, in both of these diets, myristic acid and palmitic acid were decreased in the test diets compared to the baseline diet. Is there any evidence that contradicts these two experiments? This experiment used olive oil that was very high in polyphenols, and they reported phospholipid composition, and there's no apparent increase in de novo lipogenesis. But how long do you want to rely on polyphenols to protect you from the clearly fattening effects of monounsaturated fat? It looks like at some point your luck runs out. When will your luck run out?
I'm Brad Marshall, author of the blog fireinaBottle.net. You can join the discussion on Reddit at r/saturatedfat. Follow me on Twitter at fire_bottle or on Instagram fire_in a bottle. Thanks for watching.